All right. Let's look at question number 7. So when we were doing limits, the one thing I told you guys to do is, especially when you have division, is work on the top and work on the bottom. The mistake that everybody made with it is most of you completely forgot how to deal with negative exponents. So, and those are going to come in handy when we're starting to do some other stuff after you see the power rule today. Because if I can make things into negative exponents, we get to use a nice easy rule instead of having to use the really hard quotient rule. So when we're looking at this problem, let's just look at the top. So I'm literally just going to look at that part up there. So I've got negative 2 plus h to the negative 1 plus 2 to the negative 1. So this becomes 1 over negative 2 plus h plus 1 over 2. Okay. Now that we've got it as a fraction, I can get a common denominator. So this becomes 2 over, actually, and my common denominator is 2 times negative 2 plus h, and then it's negative 2 plus h. Any questions on how I got the common denominator there? I just multiplied the denominators and multiplied the top by the opposite. So, all right, so now the top becomes just h, and the bottom is negative 4 plus 2h. All right, so now if I look at this, I can do the limit as h goes to 0 of that times 1 over h. Because if it's divided by h, then it's really the same thing as multiplying it by 1 over h. So those two things cancel out, and I'm left with 1 over negative 4 plus 2h. And if I plug in the 0 to that, I get 1 over negative 4. And that's the answer. So like I said, really the problem that most people had was dealing with the negative exponents and what to do when you get that. Any questions with that? Or are we good? Good? Yeah. All right, then we're going to go on to the new stuff. All right, so when we talked about limits and tangents and derivatives and stuff on Tuesday, remember derivatives are basically just the same thing as saying slope. It's looking at the slope of an equation at an instantaneous point instead of over time. If I have a constant term, so if I said y equals 5, what's the slope of y equals 5?
0.
It's 0, right? It's a horizontal line. Huh? Would you say positive? So it's 0. It's just, there's nothing there. So if I was looking for the derivative of that, the derivative of a constant is the same thing as saying the slope, which in this case would be 0. And that's actually true for any constant. So the derivative of any constant is going to be just 0. So there's your first derivative rule. Basically eliminates anything with no variable on it. And if any of these looked at any kind of calculus in the past, and you looked at any type of integration, integration always has plus c. That's because integration is the opposite of derivatives, and derivatives will remove the constant. So if you're going to go backwards, you have to have something for that constant. That's why you always see plus c in the integration piece, which we'll get to towards the end of the semester. All right. Now, probably the most useful of the rules, and the one that's going to come up the most often. The power rule. So this is, you can write this down. This is the actual rule. I will explain what that means by doing a couple examples and stuff like that and showing you basically there. But basically what you're going to do is you're going to take whatever the exponent is up top, move it down in front, and subtract 1 from it. So if we look at this example right here, we have x to the 6th. So my derivative of that is going to be 6x to the 5th. Because I'm moving the 6 down in front, and I'm subtracting 1 from the exponent that was there. So y equals x to the 1,000. So what's the derivative of that? Yep, 1,000 x to the 999. And remember all those things we did on Tuesday with these limit rules and everything else to do exactly that. That's why he was getting the answer so fast. All right, so the derivative of y equals t to the 4th. Yep, 4t to the 3rd. The derivative of r to the 3rd.
3r squared.
Yep, is 3r squared. Good. What's the derivative of 1 over x squared? One second. I want them to think for a minute. Think about what I said at the very beginning when we were going over examples, the problem 7 from the test. What's the thing that's going to be the most, why I wanted to go over that problem before I did this stuff? Is because I had what? Negative exponents. Now we took a negative exponent and made it positive by putting it down the bottom. You can do the opposite of that. So 1 over x squared is the same thing as saying x to the negative 2nd. And now we can do the exact same power rule that we were just doing. So that negative 2 comes down in front, and I subtract 1. So it becomes negative 2x to the negative 3rd power. So this would be negative 2 over x to the 3rd. Okay? So not everything has to be that positive exponent. The power rule works with any exponent in that situation, as long as it's a constant. All right, as long as it's a number or an integer. Okay, and actually, no, I take that back. Any actual real number, because you can do it with fractions, you can do it with e, you can do it with pi. Just can't be a variable. All right, so what about the last one I have here? I'll put this one up here. So we have y to the cubed root of x squared. So go ahead. Yeah. So that's x to the 2/3 power. So remember, when you're dealing with roots, the root is the denominator, the exponent inside is the numerator. Okay, so that's where the 2/3 comes from. Now that it's in terms of a power, I can use the power rule on it. So the derivative of that, I bring down 2/3, and then I subtract 1, so it's going to be negative 1/3. And since I'm running out of room, I'm actually going to write this on another slide. So then I have 2/3, and then that would become 1 over x to the 1/3. So I can combine all this and it becomes 2 over x to the cubed root. No, not x. 3. 3 to the cubed root of x. So that would be the final answer. So all that's the power rule. So anytime you have, when you're looking for the derivative of a variable with an exponent, you can use the power rule. It's the most common one to use. And actually the very first integral you understand is actually the reverse of that. So, any questions with the power rule? Let's do one more. This one we're actually going to find the tangent line to it at a point. So we have our equation. We have y equals x to the square root of x. So how am I going to rewrite this? This is what I said at the beginning. The number one problem that people are going to have with this, I'm pretty sure every one of you actually knows what the power rule is right now and can do it if it was a simple exponent. The problem that you guys are going to have is converting things into that so you can use it.
Turn square root of x into 1 half.
Okay?
To the power of 1 half.
So I got x to the x to the 1 half. Okay?
That will be x over 2 times x to the power of negative 1 half. Because I multiplied the 1 half by x, which is the weak coefficient.
No, can't do that.
Oh.
What's the rule for exponent? What's the exponent rule when I'm adding, when I have like bases? Add them. So 1 plus 1 half is 3 halves.
Oh.
Now that I have that, I can find my derivative of that. So bring down the 3 halves, subtract 1. Okay? All right, so now if I've got, they want the tangent line at that goes to the point 1, 1. So I need to find my slope at that point. I have my derivative, so I just got to plug in x to find my slope. So m is 3 over 2, 1 to the 1 half, which is just 3 over 2. So then we have, so y minus 1 equals 3 over 2, x minus 1. So there's my tangent line.
Like what's normal line? Oh, that's constant. That's constant, right? Normal
It's just find the equation of the tangent line and normal line. It's the same thing. The curve, right? Hold on. I don't know the answer to that question. All done. Oh, really? I do. I have to log out. Log back in. Seriously. There we go. No, that's secant. I think you're thinking about secant. Okay. Yeah.
Normal is like perpendicular to the tangent.
Oh.
So
Wouldn't that be orthogonal?
take the opposite reciprocal slope, and it's the same point. It's like the single contact point.
Oh. There we go. Learned something new today. Now let's see if it was right. Because that would be the orthogonal angle, but I've never heard it called normal. It is. Wow. I've never heard it called normal before. It's orthogonal means perpendicular. I've never actually heard it called normal. No, I learned something.
I think it's like a physics thing.
Maybe.
It's like in physics they have like normal force on that.
Oh yeah.
It's like perpendicular to the plane.
So there's the normal one. You don't even have to do anything different. You just literally got to flip and change the sign of the slope. One of the very nice things about using the point slope form of the equation, because if you had it in slope intercept form, you'd have to actually recalculate it back out. So yeah, I'll have to look up what the actual. It's got to be a physics thing. That sounds exactly right with the vectors and stuff. So good catch. All right. Any questions with that one? Next rule. The constant multiple. So if we have, basically what this rule states is the constant that's in front, so basically the coefficient, as long as it's a constant, you can pull it out and just deal with the x to the 4, or the power rule. So this one right here is the same thing as saying 3 d dx of x to the 4th, which would then be 3 times 4x to the 3rd, or 12x to the 3rd. So you can basically just pull the coefficient out and then just deal with the variable. Same thing with this one. Remember, negative signs are coefficients. That's negative 1. So I have negative 1. What's the exponent on x? 1. So I bring down the 1. And then it would be x to the what? What's right? 1 minus 1 is 0. So this is just negative 1. Now, if you think about it, that makes sense. If my equation was y equals negative x, what kind of line is that? What kind of graph is that? It's linear, right? And the slope of a linear equation is always, it stays the same. So the slope of this linear equation is negative 1. So my derivative would always just be negative 1. It's kind of the extension of the constant rule that we had at the beginning, where constants are always horizontal, so the slope is 0. Linear is just always going to be whatever number is in front of the x, which in this case was negative 1. All right, so next one. All right, so sum and difference rule. Now, you might look at this and go, oh, okay, all the basic operations work. They don't. Sum and difference, you can split them apart. Multiplication and division, you cannot. So the product rule and the quotient rule are different. Okay? So in this case, we're looking at the sum and the difference. If I have addition between terms, I can split those two terms up and do the derivative of each one independently. If I have subtraction, again, I can split the terms up and do each one independently. So I can split terms up, I can't split factors up. All right, let's see how this one actually works and makes our life a lot easier. So here's our example. So I'm going to write it in a way I never expect you to actually write it out like this, but I'm going to write it so you can see it. So in essence, what we're going to be able to do is we're going to be able to do d dx of x to the 8th plus d dx of 12x to the 5th minus d dx of 4x to the 4th plus d dx of 10x to the 3rd minus d dx of 6x plus d dx of 5. Basically, we can do the derivative of each one independently and not have to worry about like its connection to each other. So what's the derivative of x to the 8th? 8x to the 7th. What's the derivative of, well, the 12th can come down, so this will be 12. What's x to the 5th? Right, so that'll be 60x to the 4th. Move this down a little bit. Then we have this one, so we have -4, and then x to the 4th is going to give me what? 4x to the 3rd.
Negative 16x cubed.
Yep, negative 16x to the 3rd. Then we have 10x to the 3rd is 3x squared. So we've got plus 30x squared minus 6, and the x becomes what? Right, so that's just 1. So this just becomes negative 6. And what's the derivative of 5? 0. So that's my answer. Remember we did one similar to that on Tuesday? We had all the x's, the x minus h's, and well, it wasn't to the 8th power, but huh? Yeah, I would. At that point, we have to remember Pascal's triangle. I remember I was teaching summer school back when I first started teaching, and I always gave, so one of the big things I used in high school is like, I'll do beat the teacher, which all the kids love to do. And I'll say, you can bring in any problem you want. If you beat me, and if I can't solve it, and you can explain the answer, you win a prize. And it varies depending on the year what the prizes so far. So this one kid brought up on the board, he put up, it was x plus y to the 20th power. And I'm like, seriously? And I start doing it out, And I took a couple minutes. I'm like, you know what? You win if you can explain it. He walks up and writes the number on the board, and I'm like, oh, Pascal's triangle. Totally forgot about Pascal's triangle. It's like, you beat me. It happens. Hasn't happened much, but it's always fun when it does because the kids love it. It's like, because they think you know everything. It's like, no, we don't know everything. We try, but we don't know everything. Like normal, like tonight. I'm like, I've never really heard the term. We use orthogonal. It's like, I learned something new, and that's totally a good thing to do. All right. Let's keep going. Huh?
A good proof by
Partial fractions or something?
yeah.
Yeah, those are always.
Trigonometry terms.
I had to add in the fact that you have to be able to explain it because some kid brought in n versus np, which is a millennial problem and can't be solved. And I'm like, yeah, that won't work. All right, do the derivative of that for me.
What was the prize?
I don't remember what it was that year. It's like I've done gift cards. I've done like a Heart 300 on a test. I've done.
I thought you were taking like some elementary school thing. I thought you were gonna get like little pinky erasers at Disney.
Oh, God, no.
Use.
No. What was it last year? They were doing. They had to create a cart, like a fictional cart, like a wheel cart, but they had to create the wheels. They had to create the box, the actual square box in the bottom, and they had to create a three-dimensional box on top of it. And all they had was string, a piece of chalk, and a stick. They had to do this. The class that did it the fastest, all of them got $15 gift cards to Domino's. So they liked that. I'm normally pretty generous with my gifts. Oh, that's right. You guys know the trick. You're done by this point. All right. So, my original function is s equals 2t to the third minus 5t squared plus 3t plus 4. Okay? Now, my velocity, which we have to find first, because what you didn't actually find acceleration. You found your velocity. So the velocity of s is your first derivative. So that's s prime. So we did that. We got 6t squared minus 10t plus 3, and that's it. That's your velocity. Yes? Yeah, this is your position. That's velocity. And acceleration is your second derivative. So your second derivative is acceleration. So your acceleration, basically to find your second derivative, you just do the same thing again. So this becomes 12t minus 10. And now we can find the acceleration after 2 seconds by just plugging in 2. So 24 minus 10 is 14. What is it, centimeters? Well, what do they use for centimeters per second squared? There we go. That was another one of those physics things. I wanted to make sure I didn't mix up velocity and acceleration because I do mix stuff up.
Yeah, I read that as centimeters in t4, like centimeters in t seconds. So I thought it was wrong.
Oh, okay. Yeah, S is measured in centimeters, T is measured in seconds. So it's centimeters by second squared. So that's your acceleration. So when we're looking at first derivatives, second derivatives, you can do third derivatives, fourth derivatives, you can keep going. It's just the same rules apply. You just literally redo it. Okay. There it is. All right, next rule. The natural exponent rule. Okay, so we're going to look at a general rule for exponential functions in a couple classes because we need another rule to actually be able to understand why it works that way. But the natural exponential function, e to the x, the derivative of it is e to the x. It doesn't actually change. So if we're looking at this one right here, if we're looking for the derivative of this, e to the x just stays e to the x. And what's the derivative of negative x? It's just negative 1. And if I wanted to find the second derivative is just e to the x. The negative 1 disappears. And after that point, every derivative is exactly the same. So no matter what crazy problem you get with natural exponents like this, eventually it's going to become e to the x. All right. Do those two.
Conceptually, why is that?
You always have to ask the hard questions.
Well, I'm trying to like envision it like
It's
and I'm like I can't see like why that's true.
because I'm not going to write out all the rules, but I'll show you. They actually have the proof in the book. Seriously, I just logged in.
I can see the graph, and I just keep seeing the same graph over and over. I don't understand how that's.
And you do. You actually, that's exactly what happens. I'll show you. Yeah. Yeah.
I know like E is like decay.
No, E is always growth. Well, actually, let me rephrase this. E isn't always growth. E is just a number. It's just this very special number. So, all right. So, remember we had that wonderful little rule right there? That was our rule we did on Tuesday. So, if we did the x plus h and the x, so assume, in this case, they're doing the general one right here, basically. So you have x plus h minus that. We can pull out the b to the x out of these both. So and ended up left with b to the h minus 1. So because since the b to the x doesn't matter with this, because we're just doing the limit h, we can pull that out. That's in essence basically a constant at that point. So we're literally just looking at the limit of that at 0. So far, follow me so far? Okay. All right, so how did they actually explain this? Let's keep going. All right, so we got that. So they're going to the derivative as it goes to 0, they literally just estimate it because you can't get that exact number because it doesn't exist. So if we did 2, we get 0.693. If we did 3, we get 1.009 when they look at it. So that's what basically we end up getting from those. Okay, so remember we still had that 2 to the x and the 3 to the x. So if we multiply that by 2 to the x and that by 3 to the x, what ends up happening is, remember 2 and 3, so e is between those two, right? So remember the intermediate value theorem. So basically everything in between it, like if you're on either side of it, everything in between it has to exist at some point between those two. So if we have the e, what we end up finding out is that e to the h minus 1 over h is 1. That's the limit of it. And I think I actually showed you guys that at one point before, where we talked about it. I said that's going to be something you're going to need. My Calc 2 class always comes up to that and is like, where's that from? Because they never remember seeing it in Calc 1. And it's like, you did. Just didn't remember it. So that comes out to be 1 because it has to lie somewhere between those two numbers that were there. Because that was 1, because that limit was 1, if you look at these, if that's e to the x instead of 2x times 1, you're basically going to be left with just the e to the x. Okay? It's one of those weird quirks of the thing. The slope of e to the x is exactly the same as what it was. That's one of those reasons why e is that natural number. That's why it works, because it's in nature that number just keeps coming up. So, and I can say like there, like at that point, my slope is 1. At that point, my slope is e to the x. It's like it's just a matter of whatever point it is at, it's exact same as the original equation was. But it's okay. Ask the hard questions. I'll find the answer for you. There's probably a lot like more involved explanations on it. It is one of those weird, quirky little things, though. It really is. But it does work. It's been proven enough. All right. Now back to these two problems. You probably can find, like, if you go on YouTube and search it, they probably have one of those, like, knowledge videos or something like that. There's a bunch of them, like those weird math problems that they actually try to prove on how it works. I guarantee they have one for that one.
I really like seeing, like, why it works.
Yeah. No, that's fine. So, no, that's totally fine. Oh, first derivative. Just the first derivative for these. We'll have to do the second unless it asks you specifically for the second. If I think about it when I get home, I'll find a nice video that actually goes through and explains. Like,
I'm trying to, like, envision, like, the other stuff I can see, like, in stock terms, but I can't see that one. I'm trying to see, like, how would that apply to numbers? Like, how does it make something reducible? That's the other thing I couldn't see.
and E might not. Like, it doesn't, like, it might not. It's involved in other things, but it just might not.
Yeah, I know E with, like, compounding interest. But
Yes.
I can't see the derivative of compounding interest, like, being a thing. That's why conceptually I'm not understanding it yet.
Well, so in compounding interest, E is continuously compounding. So the derivative of that would be telling you what the instantaneous change in it is. The problem is when with compound interest, the instantaneous change doesn't really mean anything.
The only thing I think is like if the compounds more frequent, like the more frequent compounds, you can probably pick up the rate of change on when you change the compound periodicity.
Yeah.
That's why I gotta take it home and look it up.
Yeah.
I'm generally curious about that.
Yeah, because E is the only one that like that's continuously. Because you can change the compounding rate, like the n and all those things, and fine. But once you get to basically infinity, that's E. That's the PERT equation. Principal times e to the RT. That's when you have infinite compounding. It compounds literally continuously. There is no like literally, yeah, like literally, it's in essence infinity. Is your infinite compounding at that point. And what they found, what it is basically, if you do the limit, so as that n gets bigger and bigger, if it goes to infinity, you can do the limit of it. You're going to see that it basically goes to e. So, but play with it. So one of the things my teachers always told me in school when I came up with a question like that, go figure it out, play. And when you figure it out, let me know. It's like, because that's something like not everybody's going to be interested in, but like you're trying to connect it back to what you typically do, which is great. So, all right. So what's this one? What's 5? And that's it. The 3 disappears, and the x goes to 1. What about 7? Yep, it's literally just negative 2 to the et. That's it. All right, these two. It's like I didn't want to go into product and quotient rules tonight because I want you guys to actually have a little bit of time to decompress and actually figure out how to use these rules before we go into actually using them in other rules. So tonight will be a quicker class, but we got like 3 more problems for this one. There's my money. All right, so what do we got for this first one? Yep. So if we look at this one, we're going to go t to the negative 1 plus 2 to the negative 2. The derivative of that, we have negative 1 t to the negative second plus negative 2 t to the negative third. And then we can swap that back down, so it's negative 1 over t squared plus negative 2 over t to the third. Actually, I could make that minus. All right, what about 17? Yes. So again, we got to go through and change this. So we have x to the negative 1/2 plus x to the 1/4. So we've got negative 1/2 x to the negative 3/2 plus 1/4 x to the negative 3/4. So we get negative 1 over 2 square root of x to the third plus 1 over 4 the fourth root of x to the third. So a lot of this, again, is just being able to manipulate the problem back to be able to use those rules. And in some of these, there's going to be other ways to do it. Like you're going to, on Tuesday's class, we're going to learn the product rule, we're going to learn the quotient rule. You could do 1 over t squared using the quotient rule. But you're going to see after I show you the quotient rule why we don't want to do that. Because it's a lot longer and a lot more work to it. So if you can get things down into that power rule, it's going to make your life a lot easier. All right, these two. Yep, they're constants. So one of the things that you want to get used to is whatever the function is of, so like in this case it's z, that's the only variable. So when you're deriving it, you're doing the derivative of z. So everything else is considered to be a constant at that point when you're using it.
God, what? Wait.
Where are you?
No, it's just like my paper's cut out.
Oh, that I can't help.
Yeah, like okay, I need to.
That one. that's 26. So the one piece in this one that you have to realize is that you can split the square root of 5 and the square root of t apart. Because they're multiplied, you can easily split them apart. Make them both square roots. So I've got the square root of 5, and I made t in that one step, t to the 1/2. And this one was already separated, so that would be so then we just do the derivative of it, and then convert it back. Down a little further. All right, so this one, remember when you have fractions? The denominator can go under each of the pieces. So I have a over z squared plus bz over z squared plus cz squared over z squared. So that's a z to the negative second plus b z to the negative first plus c. Now we can do our derivatives. We can bring down the negative 2. So it's a to the negative third minus 1b. Huh? We didn't have a t. It was these. Oh, you're right, it did. Okay, sorry. I was thinking you thought I missed the plus sign. I'm like, wait, nope, you're right. I did miss the. I put it on the. Yeah, there's these. Oh, see, I don't. I like my t's look like pluses. That's why I hate using t's. And then c is gone because it's a constant. So we can clean this one up a little bit. So we have negative 2a over z to the third minus b over z squared. Are there any questions with these so far? We're good so far? All right. Okay. So here, this is where notation matters. So we've got dy dx. So this is the derivative of y in terms of x. Okay, so we've got t's and x's in this problem. So when we're looking at this derivative, this case, we're only doing the derivative of the x term. So in this one, I've got 2tx, and this one is going to be t to the third. because I'm doing the derivative of the x term. The t's are considered to be constants for all intents and purposes in this problem. And then if we did dy dt, same thing, except this time the x's are considered to be constants. So the t would be gone in this case, it would be just x squared plus 3t squared x. This is also where, I remember I told you there's different uses for the different symbols. So this is Leibniz's notation, and it works really well to be able to show those type of things, where Newton's notation might not work as well. All right, one more. All right, so find me my derivative, and then find me my tangent line at 2, 3. Just the tangent line, not the normal one this time. Thank you. So that should be your derivative. So this is something I've seen. Remember, the derivative of x is 1. You need the 1. Okay? I've seen quite often when people do it, they'll just have this. And they won't remember that because it's separate terms, you still need that 1 there. So, all right, so we're going to find our slope. So we're going to plug in 2. So slope equals 1/2. So my equation is y minus 3 equals 1/2 x minus 2. That's my tangent line. The nice thing about finding your derivative first when you're looking for tangent lines is that you can find anyone at that point. If I gave you another point, you could just plug it in and have the same thing. You wouldn't have to actually worry about going through and doing all these the extra calculations out. So it does make your life a little bit quicker there. Any problem that you want me to do another one of? Or are you guys good with this? All right, if you're good, you can go. If you have any questions, feel free to stick around and ask them. Like I said, I don't want to go on to, I want you guys to take some time to practice section 3.1 this weekend. Like go through and do some of the problems. I told you guys don't do that for the other sections I was doing because like you just saw it. Everything you would have done in that other section would have been wasted doing this. So, but I really do take some time to practice and make sure you're getting these right. Because when we go to the product rule and quotient rule next week, these rules still apply and are used. So if you don't understand this, what I'm building on top of it, you're going to get lost pretty quickly. So take some time to practice these. You too. I didn't finish regrading your test. I'll have it next week.
Oh.
I totally forgot it in my bag.
Oh.